Good morning. Welcome to the boardroom of the National Transportation Safety Board. I'm Robert Sumwalt, and I'm honored to serve as the chairman of the NTSB. Joining us this morning are my colleagues on the board, Vice Chairman Bruce Landsberg and Member Jennifer Hamady. Today we meet in open session as required by the government and the Sunshine Act to consider the pedestrian bridge collapse over Southwest 8th Street in Miami, Florida on May the 15th of last year. The bridge fell onto the street below, fully or partially crushing 8 cars, and tragically, 1 bridge worker and 5 vehicle occupants died as a result, and 10 others were injured. So on behalf of my colleagues and the entire NTSB, we'd like to offer our sincerest condolences to the family and friends of those who perished in this tragedy. And for those who were injured, we offer you the best wishes for as speedy of a recovery as possible. Today, we will discuss bridge design and construction plan errors, unique bridge characteristics and mechanisms of failure, independent peer review of complex bridge construction, shortcomings in oversight and documentation of remedial actions to control cracking, and the lack of redundancy guidelines and specifications for pedestrian truss bridges. We will determine what the initial errors were, how they could have been identified, when the signs of impending failure became known, and what preventative actions could have been taken to avoid the collapse, or failing that, to mitigate the harm it caused. And we will discuss ways that the same thing can be prevented from happening again. In today's board meeting, the staff will make several presentations. They will lay out the pertinent facts and analysis. They'll present findings, a draft probable cause, and draft recommendations. And then we on the board will question the staff. We will deliberate and vote on any proposed amendments to make sure that the report, as we adopt it today, fully accomplishes its objective, and that is to enhance safety. The public docket is available at ntsb.gov. It contains over 120 items, including over 300 photographs and over 6,000 pages of factual documentation gathered during the investigation, as well as the party submissions. And once finalized, the accident report will also be available on our website. Now, Managing Director Sharon Bryson, if you'll kindly introduce the staff.
Good morning, and thank you, Mr. Chairman. I have a few administrative announcements prior to announcing staff and beginning the meeting. I would like to request that everybody in the room, just as a reminder, could you please silence your mobile phones and other electronic devices? And also, there are 2 exits from the boardroom. Obviously, in the front, they're marked with the exit signs. You should go down the stairs and through the door. It will take you into hallways of the lower level of the office building before you depart the facility. The other exit is the way that you entered the boardroom. Go up the aisle, proceed out the glass doors where you entered, up the stairs, and exit through the large glass doors to the outside. Once you're exited, turn left and follow the sidewalk to the end of the street. The NTSB staff and security personnel will direct you in the event of an emergency. We will also direct you when it's safe to return to this room. There is also, should we need it, an AED device in the lobby of the boardroom, and the security personnel can contact 911 if necessary. If you have any questions or concerns, please don't hesitate to speak with anyone on the NTSB staff. So seated at the panel this morning with me, unless otherwise noted, are staff members from the Office of Highway Safety. On the first row, starting to my right, is Dr. Robert Malloy. He's the director of our Office of Highway Safety. Ms. Michelle Beckjord is the project manager for this accident. She is also from our Office of Highway Safety. Mr. Robert Aceta is the investigator in charge. Ms. Adrienne Lamb is from the Materials Group in our Office of Research and Engineering. Mr. Steve Prouty is helping us with bridge factors, and he is also from our Office of Highway Safety. Dr. Dan Walsh or Mr. Dan Walsh, sorry, is also working on bridge factors as well. Seated behind me is Ms. Darlene Hatchett. She's our Director of the Office of Safety Recommendations and Communications. To Darlene's right is Kathy Silva. She's our General Counsel. To her right is Barbara Check, the Deputy Director for our Office of Research and Engineering. To Barbara's right is Mr. Kenny Bragg, our Human Performance Investigator. To Kenny's right is Dr. Tom Barth, Survival Factors. And to Tom's right is Ms. Julie Perot from our Office of Safety Recommendations and Communications. Seated in the very back row is Mr. Mark Banyard. He's going to be assisting with audiovisual and timing. And to Mark's right is Ms. Gwen O'Regan, who is the editor on this report. The presentations will begin with a collapse overview provided by Robert Aceta, the investigator in charge.
Good morning, Chairman Sumwalt, Vice Chairman Landsberg, and Member Hamady. Today's staff is presenting for your consideration a report of the Florida International University, FIU, pedestrian bridge collapse that occurred in Miami, Florida on March 15, 2018. This is a map showing the location of the FIU pedestrian bridge 11 miles west of downtown Miami, with insert maps showing a close-up view of the intersection of Southwest 8th Street and Southwest 109th Avenue and Miami's location in South Florida. This is an overview of a rendering of the pedestrian bridge if it had been completed, showing the South Pier, the main span, the 10 diagonal steel pipes, the upper pylon pier, the back span, and the North Pier. The shaded area shows the parts of the bridge that had not yet been constructed. This figure shows the canopy, truss members numbered 1 through 12 from the south end toward the north end, the deck, the south and pylon diaphragms, the South Pier, and the pylon pier that were in place on the day of the collapse. Staff has prepared an animation that provides additional details of the main span and the events leading up to the collapse. Please play the animation.
On Thursday, March 15, 2018, the Florida International University pedestrian bridge collapsed, killing 6 people and injuring 10 more. The collapse occurred 11 miles west of downtown Miami in Miami-Dade County, Florida. The Florida International University pedestrian bridge was located on the west side of the intersection of Southwest 8th Street and 109th Avenue. The elevated pedestrian bridge would have connected the university with the city of Sweetwater by extending over Southwest 8th Street and the parallel running Tamiami Canal. The first section of the bridge constructed was the span across 8th Street, and that was the section that collapsed. The bridge section was built on the ground in a construction yard adjacent to the roadway, and then moved onto support piers using 2 self-propelled modular transporters. Building the bridge alongside the road before moving it into place is a construction process called accelerated bridge construction, which reduces on-site construction time and minimizes traffic impact. The overall conceptual design had the appearance of a cable-stayed bridge. However, the central pylon and steel pipe stays were not load-carrying structural elements. Instead, the functional design was a truss structure that was unusual for being constructed out of reinforced concrete and also for having the truss members aligned in a single plane. The bridge section that spanned Southwest 8th Street was 174 feet long and weighed 950 tons. It contained a deck, vertical and diagonal truss members, and a canopy. The truss members were numbered 1 through 12 starting from the south end of the bridge. The design of the bridge was non-redundant, meaning that failure of an individual truss member would cause collapse of the bridge. The concrete for the section was poured in 3 stages. First the deck, then the vertical and diagonal truss members, and finally the canopy. Separate pours form discontinuities in concrete structures called cold joints. In this bridge, cold joints were located between the deck and the truss members, and between the truss members and the canopy. Within the concrete, reinforcement was provided by steel bars and larger diameter steel post-tensioning rods. These rods were pulled in tension and locked into place after the concrete had cured in order to ensure that the concrete was loaded in compression. The post-tensioning rods and steel reinforcing bars were to carry the tension loads of the completed bridge. Before the bridge was moved onto the piers, truss members 2 and 11 were post-tensioned in the construction yard to counteract the tensile forces developed while the ends of the bridge hung over the transporters when the span was moved. After the bridge was placed onto the piers, truss members 2 and 11 were under compression, and the post-tensioning rods were detensioned. Before the bridge section was moved into position on the piers, cracks were observed in the concrete at and adjacent to the cold joint between the deck and members 11 and 12. The cracking got worse once the bridge section was placed on the piers. These cracks continued to grow over the next 5 days, and numerous photographs documented the progressive cracking in the structure. In response to the cracking, a decision was made on the day of the collapse to retension the steel rods in truss member 11. Workers were retensioning member 11 when the collapse occurred. The road was not closed while this work was taking place. The bridge section was placed onto the piers on the morning of Saturday, March 10, 2018. It collapsed 5 days later on the afternoon of Thursday, March 15, 2018. The collapse began at the north end of the bridge, initiating at the cold joint between the deck and truss members 11 and 12. Large shear forces and insufficient reinforcement across the cold joint at this location led to the steadily growing cracks and structural failure. 1 bridge worker was killed in the collapse, as were 5 people in vehicles under the bridge. 5 bridge workers and 5 other people were injured.
As mentioned in the animation on March 15, 2018, at approximately 1:46 p.m., the main span was in place on the South Pier and Pylon Pier when it experienced a catastrophic failure in the truss member 1112 nodal region and bridge deck as shown in this figure. At the time of the collapse, vehicular traffic was stopped below the main span for a red light at the traffic-controlled intersection with Southwest 109th Avenue. A construction crew was also working on retensioning the internal post-tensioning rods, also called PT rods, within the main span of the truss member 11 that connected the bridge canopy and the deck at the Pylon Pier. The animation also stated that a 6-person construction crew was working on the bridge at the time of the collapse. 1 worker was fatally injured, 4 were seriously injured, and 1 received minor injuries. In addition, 7 occupied vehicles stopped below the bridge were fully or partially crushed. 5 vehicle occupants were fatally injured. 2 was seriously injured, and 3 received minor injuries. An 8th vehicle, parked in the westbound lanes, was unoccupied and partially crushed. This slide shows the NTSB Investigative and On-Scene Staff. There are a total of 19 NTSB staff members that contributed to the on-scene investigation. The following slides show the report development staff. There are a total of 14 NTSB staff members that contributed to the report development of this investigation. There were more than a dozen party members involved in this investigation, 8 federal, state, city, and law enforcement agencies, and 5 private industry party members also participated in the investigation, listed here alphabetically. This slide is an organizational chart showing some of the parties that were involved in the FIU Pedestrian Bridge project. The Florida DOT was to assist FIU in the receipt and distribution of funds that FIU received from the U.S. Department of Transportation to construct a new pedestrian bridge over Southwest 8th Street, and subsequently the Florida DOT delegated its project oversight to FIU, and if necessary, the Florida DOT was called in for consultation. FIU then hired MCM to construct the bridge, and Bolton Perez and Associates Consulting Engineers to administer, monitor, and inspect the bridge as it was constructed. MCM, the design builder, hired FIGG Bridge Engineers Incorporated, or FIGG, to provide professional design and engineering services. And FIGG entered into an agreement with the firm Louis Berger to perform an independent peer review of the bridge plans. Staff has prepared 6 presentations for today's board meeting. During Ms. Lamb's presentation, she will discuss the evidence that was collected in support of the investigation and the testing and analysis of that evidence. Presentations 2 through 6 will be presented by Mr. Prouty and Mr. Walsh. Their presentations will discuss the safety issues that were identified in the investigation. Ms. Lamb, please proceed with your presentation.
Good morning. My presentation will cover 3 areas: the evidence collected from the collapsed main bridge span, the results of testing on the collected evidence of bridge concrete and steel materials, as well as construction equipment, and finally, the results of the surface roughness examination of the concrete cold joint between the deck and members 11 and 12. After the collapse, the north end of the main bridge span remained largely intact. Shown here is a side-by-side comparison of renderings of the structure in pre- and post-collapse positions. As you can see, when the bridge collapsed onto Southwest 8th Street, this section had rotated approximately 90 degrees downward from the pylon pier. The north end of the structure was determined to be the initiating location of the collapse, as will be discussed in the next presentation by Mr. Prouty. As part of our investigation, the NTSB removed large pieces of evidence from the collapse site for examination and testing. These sections included blister 10-11 that contained anchorages for the member 11 post-tensioning rods, bridge truss member 11 and truss member 12, and the node region of members 11 and 12 where they connected to the bridge deck. Shown here in the top left photograph is the north end portion of the bridge deck recovered from the scene. In this view, members 11 and 12 have already been removed and would have been positioned in the locations indicated. The yellow arrow points to the north face of the piece, seen in the photo on the right. This north face had a pattern of damage, shown between the red dashed lines, emanating from the node where members 11 and 12 met the bridge deck. In addition to the large concrete pieces, numerous other specimens were collected from the bridge for further evaluation. The image shown is a top-down view captured by a drone of the collapsed bridge. The specimens collected for testing included concrete core samples from the deck and canopy. Additionally, concrete cylinders made during the construction pours of the structure were also recovered for testing. Post-tensioning hydraulic equipment being used on the structure at the time of collapse was also retained for examination. Steel PT rod and reinforcement bar specimens were among the evidence collected. This included the south PT rod that was inside member 11, circled in the right image. Steel reinforcement bar specimens of varying sizes were collected from the interior of member 12, indicated by the circle in the left image, as well as from the bottom of member 11 and the north end of the bridge deck section in the node 11-12 area. The concrete and steel specimens were examined and tested at Turner Fairbank Highway Research Center, or TFHRC. Testing showed the compression strength and internal structure of the concrete met the specifications of the build plans. In addition, while not specified, the concrete performed as expected in tensile tests. A steel PT rod from member 11 and an unused PT rod collected from the scene were tested for strength and chemical composition. Both steel rods met specifications. Finally, the bridge contained steel reinforcement bars, also called rebar, of various sizes. The tested rebar all met the required strength specifications. In summary, the materials testing revealed no issues with the quality or performance of the construction materials. The post-tensioning hydraulic jack collected from the scene was also examined and tested at TFHRC. Examination of the jack revealed its internal components were in a position consistent with performing a tensioning operation. Testing results determined the equipment operated correctly and had the capability to apply the full range of loads in accordance with the specified calibration. Finally, I will discuss the surface roughness examination of the north end of the bridge deck. As described in the animation, cold joints are locations where different concrete pours share a surface, which in the FIU bridge occurred where truss members connected to the deck and canopy. Cold joints are commonly roughened during construction to enhance their performance. The Load and Resistance Factor Design, LRFD, bridge design specifications written by the American Association of State Highway and Transportation Officials, or AASHTO, calls for roughened concrete to have an amplitude of 0.25 inches. Florida Department of Transportation, or Florida DOT, does not stipulate a minimum roughness amplitude in their construction specifications. FIGG's bridge design was calculated for the cold joints to meet the AASHTO specification, yet their construction plans referenced Florida DOT and did not include a note for node 11-12 to specifically meet AASHTO's cold joint surface preparation. Post-collapse, portions of the deck under member 11 and the bottom of member 12 were collected for examination. The graphic and photo show the only portion of the cold joint remaining on the bottom of member 12 outlined in orange. The cold joint surface on the deck under member 11 and on the bottom of member 12 were laser scanned and evaluated. This graphic is a visualization of part of the mathematical analysis used to determine surface roughness. The top shows the scanned cold joint surface on the bottom of member 12 in black. The surface roughness profile of the red line across the scanned area is shown in the bottom. The profile can be thought of as the peaks and valleys on the scanned surface across that red line. The mathematical analyses calculated the average surface roughness below 0.25 inch amplitude for both the member 11 and member 12 surfaces examined, which indicates the coal joint was not intentionally roughened per AASHTO specifications. However, even if the coal joint of node 1112 had been roughened to a 0.25-inch amplitude, this likely would not have sufficiently increased the structure's capacity to counteract the demand load, meaning the bridge was still under design and could have still failed. The actual mechanisms of this failure will be discussed next by Mr. Prouty. In summary, the NTSB and Turner Fairbank Highway Research Center testing determined the concrete material properties, the steel PT rod mechanical properties, and the reinforcement steel material properties all met the requirements of the FIGG Bridge design. Testing also confirmed the hydraulic equipment was operating normally while performing the post-tensioning operation on the day of the collapse. Finally, the examination of the truss member 1112 node coal joint surface found it was not intentionally roughened. Regardless, even if it had been performed, intentionally roughening the member 1112 coal joint surface likely could not have prevented the failure of the bridge. Mr. Prouty, please proceed with the next presentation.
Good morning. In this presentation, I will explain the mechanisms of failure that were key to the collapse of the bridge. This presentation will begin by discussing a few background concepts that should be helpful in understanding the mechanisms by which the bridge failed. I will then describe some of the initial indicators of structural distress coinciding with the member 11 and 12 coal joints with the deck, the load path changes that occurred during the construction of the bridge, remedial actions that were taken in an effort to address the structural cracking, and the collapse of the bridge. This slide shows an outline of the north end of the bridge main span. Truss members can carry axial loads, which are forces aligned along the axis of the member. These axial forces can either be in the form of tension or compression. These axial forces can be broken down into both horizontal as well as vertical components. The magnitude of each of the components is related to the angle through which the force is acting. In this example, the horizontal component, shown in red, is larger than the vertical component, shown in orange. Back in the context of the bridge, the vertical or downward component force provides a clamping effect across the coal joint between member 11 and the deck. The horizontal or northward force provides a shear force at the coal joint, which is trying to push the bottom of member 11 to the north. Before we begin discussing the first signs of distress, I would like to point out that some cracking in reinforced concrete structures is both normal and to be expected, as tensile forces are transferred from the concrete to the reinforcing steel inside the structure. As we'll talk about more in my next presentation, the cracking that was observed in this structure, however, was 40 times larger than what is typically considered acceptable, and these cracks were also located in a critical nodal region. Prior to moving the main span onto the piers, the falsework that provided continuous support along the length of the span was removed sequentially from the center of the span outward towards the ends, as shown in the photo. During this process, on February 24th, a loud, distinct concrete cracking noise was heard, and, as shown in the photo on the right, a crack was found in the member 11-12 nodal region near and at the intersection of truss member 11 and the deck. As detailed on the FIGG construction plans, 8 size 7 rebars were to cross the coal joint under member 11. Although all 8 rebars were present in the structure, the crack passed above the southernmost 2 size 7 rebars, circled in the figure. This circumstance is attributable to the FIGG design containing a detailing scheme wherein the southernmost 2 rebars were not anchored on both sides of the critical horizontal shear plane at the base of member 11. Because the crack bypassed 2 of the 8, or 25% of the rebars that crossed the coal joint, the cross-sectional area of reinforcing steel, which was intended to offer resistance to the northward thrusting interface shear forces at the base of member 11, was also reduced by 25%. The next load path variation occurred when the support configuration changed as the bridge was moved to its permanent support piers. For the pylon pier at the north end of the bridge, 4 discrete shim stacks were placed between the diaphragm and the pylon pier. 2 shim stacks each were located to the east and west sides of the bridge centerline, as shown in the figure. No supporting shim stacks were located directly beneath the truss center line in the area between the vertical pipe sleeves that passed through the diaphragm. This support configuration was in direct contrast to the configuration in the casting yard that consisted of full width support under the end diaphragm. The post-tensioning rods in truss member 11, as shown in the figure, served multiple purposes during the movement of the main span. The forces imparted by the rods onto member 11 counteracted the tensile forces in the member, while the north and south ends of the bridge were cantilevered beyond the support points used by the self-propelled modular transporters. As previously mentioned, post-tensioning rods also generated both a beneficial vertical clamping force across the horizontal interface shear plane at the base of member 11 and a detrimental horizontal shear force across the base of members 11 and 12 in a northward direction relative to the deck. Given that the angle of member 11 relative to the deck was approximately 32 degrees, the magnitude of the post-tensioning induced horizontal shear force was about 60% larger than the vertical clamping force. Immediately after the removal of post-tensioning in member 11, the concrete distress previously observed in the member 11-12 nodal region significantly increased and was apparent in two observed structural behaviors. First was flexural cracking on the north face of member 12, and second was cracking consistent with interface shear along much of the node. The construction of the member 11-12 nodal region included 5 hollow pipes which acted as voids within the concrete mass. As shown in the figure, one horizontal drain pipe ran underneath the deck and through the diaphragm. 2 vertical pipes passed through the deck and diaphragm along the east face of member 12, which are also shown in the figure. 2 additional vertical pipes ran through the deck and diaphragm along the west face of member 12. These pipes were oriented and located similarly to the pipes along the east face of member 12, but are not visible in the figure. The inclusion of these 5 hollow pipes was significant to the structural performance of the 11-12 nodal region. The voided areas caused by these hollow pipes would have exhibited a lower stiffness than the surrounding concrete, and as a result, the node would have been less able to resist the northward thrusting shear forces. The concrete surrounding these pipes would have been subjected to higher stress concentrations and the unanticipated redirection of the load path. The placement of the reinforcement in members 11 and 12 was consistent with the construction plans. Investigators determined that 2 primary mechanisms temporarily resisted the northward dislocation of the nodal region relative to the deck. First, the lower portion of member 12, whose bottom end was connected to the diaphragm and whose top end was connected to the canopy, and second, the steel reinforcement that crossed the shear planes under member 11 and beside member 12 as shown in the upper figure. The column steel reinforcement in member 12 was in place from the level of the drain pipe near the bottom of the diaphragm to a few feet above the deck. The vertical reinforcement with lap splices beginning just above the deck level and the confinement reinforcement as shown in the lower figure combined to create a concrete column that was capable of buttressing much of the load being driven northward by member 11. The bottom figure provides an overhead perspective of the reinforcing steel within member 12, showing 3 size 11 bars circled in orange running vertically along the south face, and 3 size 7 bars circled in yellow running vertically along each of the north, east, and west faces of the member. In order to address the increased cracking that occurred between March 10th and March 13th, 2018, FIGG directed MCM to immediately place a shim on March 13th under the diaphragm in the area along the bridge center line between the existing 2 innermost shim stacks as shown on the screen. MCM was told that lifting or jacking of the bridge was not required, thus the shims were to be manually inserted without lifting the bridge to rebalance the loads between the 5 shim stacks. Without lifting the bridge to rebalance the loads, however, no sizable loads could have been redistributed into the new shim stack. The placement of additional shims under the center line of the bridge was not part of the original plans and was a remedial action ordered in an attempt to address the cracking. Despite not knowing why the concrete cracking was occurring, an attempt was made to address the cracks observed in the structure. The FIGG Engineer of Record, or EOR, called for the retensioning of the PT rods in truss member 11 on March 15th. As they were finishing the retensioning, the bridge collapsed. After the collapse, the Engineer of Record stated in an interview with NTSB investigators that the purpose of restressing member 11 was to address the cracking and bring the main span back to what he determined would have been a pre-existing condition as it was in the casting yard. Similar to the placement of the additional shims under the center line of the bridge, the retensioning of member 11 was not part of the original plans and was a remedial action ordered in an attempt to address the cracking. The NTSB determined that the retensioning of member 11 increased the demand across the interface shear surface, pushing the concrete beyond its limits and causing it to fail along 3 distinct failure planes. On the screen, one of the failure planes is identified by the solid red line, which approximates the east-west oriented failure plane. The other 2 failure planes are identified by the red crosshatched region, which approximates the north-south oriented failure planes in the deck, and were aligned along the east and west faces of member 12. This slide shows an outline of the north end of the bridge main span on the left and an outline of the south end of the planned bridge back span on the right. The back span is shown here for illustrative purposes only, as it had not yet been constructed at the time of the collapse. As before, each of the axial forces in diagonal members 11 and 14 can be broken down into their component forces. Shown here in red are the horizontal components for each of the diagonal members. Once the back span had been constructed, the horizontal force component from diagonal member 14 would have been pushing towards the south, helping to counteract or resist the northward force in truss member 11. Because the back span had not yet been constructed, however, the northward shear force caused by the retensioning of member 11 was able to push through the bottom of member 12, causing the collapse of the bridge. In summary, the FIGG design resulted in less reinforcing steel available and diminished resistance to the critical interface shear demand, which contributed to the collapse of the bridge. The member 11-12 nodal region contained numerous non-structural voids within the concrete that led to destabilization and overstress of the node. The concrete distress significantly increased with the post-tensioning in member 11, and the retensioning of member 11 provided additional force across the already compromised interface shear plane, resulting in the collapse of the bridge. In my next presentation, I will describe the limited evaluation of the structural distress performed by the bridge design engineer of record and the remedial actions taken in an attempt to control the cracking. This presentation describes the scale of the concrete's cracking in the member 11-12 nodal region, FIGG's remedial plan to retension member 11, and responsibilities and authorities among parties to close a bridge under construction when it is deemed unsafe. I will also discuss Florida DOT's oversight of local agency program, or LAP, projects. During the 3 weeks preceding the bridge collapse, the structure displayed notable cracking of the reinforced concrete. As I mentioned in my last presentation, I would like to remind everyone that some cracking in reinforced concrete structures is normal and even to be expected. The extensive large cracks observed in the member 11-12 nodal region, however, should have been recognized as being abnormal for a reinforced concrete structure. This slide graphic is to illustrate the number and location of cracks captured in the numerous photographs of the north end of the bridge taken during the days leading up to the failure. In a pre-stressed reinforced concrete element, cracks up to 16 thousandths of an inch wide are often considered generally acceptable, depending on the location of the cracks and the purpose of the structure. Some of the structural cracks located in the critical regions of the pedestrian bridge on both sides of node 11-12 were up to 3/4 of an inch wide, more than 40 times larger than what is considered to be generally acceptable. This scale of cracking in this type of structure is a clear indication that the intended load-resisting mechanisms were failing. On March 15th, FIGG presented a remedial plan to retention member 11 to Florida DOT, FIU, MCM, and Bolton Perez. This action was not shown on the FIGG design plans, and the post-tensioning inspection contractor was not notified in advance that the work was being performed and therefore was not on site. Based on the investigation, staff concluded that the retensioning of member 11 would not have returned the main span to a pre-existing condition for the following reasons. First, the main span was supported in a different manner in the casting yard versus how it was supported while spanning Southwest 8th Street. Specifically, the main span's north diaphragm was supported across its entire width in the casting yard and was supported only on discrete shim stacks while spanning the roadway. This difference in support conditions would have changed the internal load paths within the structure. Second, the severity of the cracks in the member 11-12 nodal region after the move and detensioning on March 10th had grown significantly as compared to the small cracks that appeared on February 24th in the casting yard. Finally, the significant increase in progression of the structural cracks clearly indicated that the steel reinforcement was yielding and/or fracturing. For these reasons, staff concluded that retensioning member 11 was a change to the design plans that should have been reviewed, signed, and sealed by a professional engineer, none of which were done. Shown on the next two slides are screen captures of select presentation slides that were presented by the FIGG engineer of record to Florida DOT, FIU, MCM, and Bolton Perez during the meeting held on the morning of March 15th, 2018. During this meeting, it was stated that FIGG had conducted supplemental calculations and concluded that there was no concern with the safety of the main span suspended over the roadway. During the same presentation, it was also stated, as shown on the slide, that FIGG was unable to replicate the concrete distress in their engineering analysis, and indicating that they were minor, he recommended that the cracks just be filled in with an upcoming concrete pour. Despite the FIGG engineer of record acknowledging that he was unable to identify the origin or reason for the cracking, this remediation plan was implemented because, according to him, the retensioning of member 11 would have brought the main span back to its pre-existing condition. Immediately after retensioning member 11, the bridge collapsed. All parties involved in the lab project to build the pedestrian bridge were aware of the cracks and their progression, including FIU, Florida DOT, FIGG, MCM, and Bolton Perez. The remedial work, as FIGG presented at the March 15th meeting, called for placing workers on the structure without identifying the origin or reasons for the formation of the structural cracks. Without the post-tensioning inspector available, Bolton Perez could have exercised their authority to suspend the work, acting collectively with Florida DOT and FIU. In fact, all the parties that were present at the March 15th meeting had implied authority under the terms and conditions of the contract, allowing them to suspend the work on the bridge for safety reasons. However, none of them acted on that authority. On past Florida DOT projects, shutting down a bridge project or taking other related safety measures during construction, while not typical, has occurred. Florida DOT was able to provide several recent examples in which bridges were closed during the construction process in order to protect the traveling public. In these instances, the engineer of record or the construction engineering inspector directed the contractor to close the bridge until the action could be taken to address safety concerns. The final safety issue I would like to discuss is Florida DOT's oversight of local agency programs or LAP projects, such as the FIU Pedestrian Bridge. LAP projects are those in which a local agency is certified by Florida DOT to plan, design, construct, inspect, operate, and maintain a LAP project. LAP projects are ideal for low-risk ventures. However, in 2014, FIU received full certification as a local agency from Florida DOT, even though it had no professional engineers on staff and relied solely on FIGG, MCM, and Bolton Perez to make all engineering-related decisions, such as closing a bridge when structural cracks were first detected. In addition, because the pedestrian bridge was a unique and complex design, Florida DOT should have provided more oversight as the supervising agency for this project, ensuring that it was designed and constructed according to specifications. In summary, The distress in the main span structure was active, particularly the member 1112 nodal region, and continued to grow significantly before the collapse. This distress and structural cracking was documented by FIU, FIGG, MCM, Bolton Perez, and Florida DOT. None of these parties took the responsibility for declaring the cracks were beyond any level of acceptability and did not meet Florida DOT standards. Moreover, Bolton Perez, along with the Florida DOT and FIU, had the authority to direct or authorize partial or complete road closure on Southwest 8th Street to the public. However, none acted to close the road, which contributed to the severity of the bridge collapse. NTSB staff is proposing new recommendations to Florida DOT to strengthen the requirements in LAP agreements regarding the authority to immediately close a bridge when structural cracks are first detected, to require Florida DOT to monitor and inspect all LAP bridge projects with uncommon designs, and that a certified local agency have adequate staff trained and experienced in administering these types of uncommon bridge designs. Mr. Walsh will now discuss errors that were made in the bridge design.
Good morning. In this presentation, I will explain the bridge design errors performed by FIGG that led to a severe underestimation of demand and significant overestimation of capacity at the 1112 nodal region of the structure that led to the collapse of the FIU pedestrian bridge. Let me walk you back to why the bridge failed in the first place. The location of where the pedestrian bridge failure occurred was at the 1112 nodal region. This still image extracted from the in-vehicle video of the collapse captured the concrete blowout at the 1112 nodal region at the deck. The pedestrian bridge collapsed because of design errors performed by FIGG in which the demand placed on the 1112 nodal region exceeded the capacity of the structure. This figure shows a simplistic view of loads imposed on the pedestrian bridge. Demand is what the bridge needs to support, and capacity is what the bridge is able to support. The American Association of State Highway and Transportation Officials Load and Resistance Factor Design, or commonly known as AASHTO LRFD, was the specification used in the design of the pedestrian bridge. The AASHTO LRFD states that bridges shall be designed to achieve the objectives of safety, constructability, and serviceability. These objectives are met through the theory of reliability based on current statistical knowledge of loads and structural performance. In LRFD design, the demand is conservatively estimated and the capacity is proportioned to reliably resist those loads. During the design process, FIGG used 4 analytical models to determine the demand on the bridge: a 2-dimensional model of the completed 2-span bridge, a 2-dimensional model of the main span supported at specific locations during transport, a 3-dimensional model of the main span simply supported at the South Pier and Pylon Pier, and a 3-dimensional model of the main span fixed support that was altered to replicate the completed condition. The figure to the right illustrates the axial forces at the 1112 nodal region. The vertical component is the compressive or clamping force P sub C that contributes to interface shear resistance. As shown by the red arrow, the horizontal component shearing force is what caused the concrete blowout at the 1112 nodal region. FHWA provided technical expertise and resources to evaluate the bridge design models. FIGG's use of the main span fixed support model estimated the interface shear demand at the 1112 nodal region to be 978 kips, a severe underestimation of the demand compared to FIGG's completed 2-span model of 1,990 kips and FHWA's model that was performed post-collapse of 1,835 kips. This bar graph shows the interface shear demand generated from FIGG's models compared to the post-collapse check. The forces generated from FIGG's completed two-span model, shown in green, generated the largest forces for the nodal regions at the north and south ends of the main span. Despite the completed two-span model generating the largest forces, for reasons unexplained, the FIGG design exclusively used the results from the main span's simple and fixed support model shown in red and highlighted at the 11-12 nodal region. FIGG's use of only the main span simple and fixed support model outcomes compared to FHWA's post-collapse check shown in blue resulted in the underestimation of interface shear demand by 49% at nodal region 1-2, 43% at nodal region 2-3, 91% at nodal region 10-11, and 46% at nodal region 11-12. The interface shear capacity is generated from the amount of permanent compressive loading perpendicular to the interface, or P sub C, and the amount of reinforcing steel crossing the interface surface. In determining the permanent compressive loading, the load factor on the dead load of structural components can be taken as either 0.90 to generate a conservative estimate or 1.25 to generate a non-conservative estimate. FIGG inappropriately used a load factor of 1.25 in its P sub C calculation, amplifying the permanent compressive loading. However, the FHWA strongly recommends the 0.90 factor on dead load when determining a minimized interface shear capacity value. Because FIGG did not use the conservative load factor, its bridge design calculations led to a significant overestimation of capacity at the 11-12 nodal region, with insufficient reinforcing across the interface shear surface. In summary, the FIGG design made significant errors in the determination of loads, choosing the wrong interface shear demand value, leading to a severe underestimation of demand. In addition, the FIGG design chose the wrong load factor in calculating the permanent compression loading, or P sub C, leading to a significant overestimation of capacity at the 11-12 nodal region. Staff is proposing new recommendations to AASHTO and FHWA, who as leaders in setting technical standards for highway bridge design and construction should provide additional guidance to bridge designers on determining reasonable estimates for the demand and capacity on structures. In this presentation, I will discuss the following issues. 1, the Florida DOT requirements for an independent peer review of complex bridge designs. 2, Louis Berger's lack of qualification to conduct a peer review. And 3, the inadequacy of Florida DOT's oversight of the peer review process. The first issue I will discuss is the pedestrian bridge required an independent peer review because it was a complex concrete bridge. Florida Code establishes the qualification standards for peer review firms specifically by the design work type, and that peer review firms must be pre-qualified by Florida DOT. If a firm applies for pre-qualification and is approved, Florida DOT issues a pre-qualification letter specific to the approved work type. Because of the complex FIU bridge design, any pre-qualified firm was required to have at least 3 professional engineers on staff, with each engineer having a minimum of 5 years' experience specific to complex concrete bridge design. In addition, Florida DOT requires the independent peer review be performed by an engineering firm with no involvement in the project. When FIGG was hired to design the FIU bridge, their technical proposal stated the independent review would be performed by a different design office within FIGG. However, this was not permitted by Florida DOT, as this did not meet the requirement for an independent firm with no involvement in the project. As such, FIGG then hired an outside review firm, Louis Berger, at a late stage in the Florida DOT review process of the FIU project. Per Florida DOT, this peer review by Louis Berger was expected to be a comprehensive, thorough, independent verification of the original design work and not simply a check of the FIGG's design plans and calculations. The second issue I will discuss is that Louis Berger was not pre-qualified to perform the independent peer review on the FIU bridge. While Florida DOT records indicate that Louis Berger applied for this work type in 2013, Florida DOT did not approve the application as Louis Berger lacked the required 3 professional engineers with 5 years of complex bridge design experience. Post-collapse, at the request of NTSB investigators, Florida DOT did confirm that Louis Berger had erroneously been listed on the Florida DOT website for this work type due to a technical error. However, according to Florida DOT, its website is for informational purposes only and is not intended to be used as a substitute for due diligence. Although not qualified to perform the review, Louis Berger did review the FIU bridge design. However, Louis Berger's review was inadequate as it was not a comprehensive and thorough independent verification of the original FIGG work. While Louis Berger did analyze the bridge structure, they did not analyze the design in the different stages of construction and nodal areas. According to Louis Berger, this would have exceeded the budget and required additional time. This in part was due to FIGG's failure to initially provide for an independent review as required by Florida DOT, which significantly shortened the time period needed for a thorough peer review. Louis Berger's inadequate peer review of FIGG's design plans did not identify the significant underdesign of truss member 1112 nodal region. This underdesign led to the bridge structural failure and collapse. Finally, the third issue I will discuss is the Florida DOT oversight of independent peer reviews. Florida DOT requires bridge plans at the 90% stage be certified. The same review firm then also certifies the plans once they reach 100% completion, and the firm signs and seals a certification letter. However, on the FIU project, Florida DOT allowed Louis Berger to skip the 90% plan submittal without a certification, citing it was an in-progress review. Florida DOT missed a critical step in their oversight when it permitted Louis Berger to skip the 90% plan submittal, failing to verify the firm was pre-qualified. Also, when Louis Berger signed and sealed the 100% plan submittal package, Florida DOT failed to verify Louis Berger was pre-qualified to perform this work. In summary, Louis Berger did not have the appropriate qualification to perform the review and was not permitted by Florida DOT to certify the FIGG plans. FIGG's failure to adhere to the Florida DOT's requirements in initially contracting for an independent peer review firm and Louis Berger's inadequate peer review resulted in significant errors in FIGG's design to go undetected. While Florida DOT misidentified Louis Berger as qualified to perform this level of work and has since corrected their website, Florida DOT failed to verify that Louis Berger was pre-qualified when they accepted the 100% plan submittal for the FIU bridge. Staff is proposing recommendations for verification of independent peer review firm pre-qualifications and for peer reviews to specifically check and verify all nodal connection forces in complex bridge designs. In my final presentation, I will discuss the need for national and state guidelines on redundancy for uncommon bridges that include concrete structures. I will also discuss FIGG's misinterpretation of redundancy for the FIU pedestrian bridge. The upper figure illustrates a rendering of the FIU bridge. The single row of diagonal supports that extended down the center line of the structure created a situation in which each member was non-redundant, or any single component failure would cause failure of the bridge. The lower figure is a photo of a typical truss design that has two sets of regularly spaced vertical truss pieces running along each side of the bridge with top lateral bracing. Reinforced concrete truss bridges are rare, and research found no other design similar to the FIU pedestrian bridge. Although truss bridges can be made from a variety of construction materials, they are typically constructed of steel because of the inherent need for trusses to carry both compressive and tensile forces. Redundancy can be provided in one or more of the following ways: load path redundancy, as discussed in Mr. Prouty's presentation on mechanisms of structural failure, and internal redundancy. During post-collapse interviews, FIGG believed the pedestrian bridge was redundant because longitudinal and transverse tendons were located in the deck and post-tensioning rods were located in the diagonal truss members as shown in the figure to the right. Although this is a true statement about the structure's internal redundancy, it did not address the structure's lack of load path redundancy, which is a critical condition in which alternative load paths must exist to redistribute and carry the load in the event of a failed member to prevent collapse. Although the AASHTO LRFD bridge design specifications addresses the design of steel truss structures and defines redundancy and redundant members, it provides a limited discussion on the redundancy in the design of concrete structures. In addition, the LRFD guide specifications for the design of pedestrian bridges does not provide a discussion regarding redundancy. Likewise, on a state level, the Florida DOT Structures Design Guidelines also does not discuss redundancy in the design of concrete structures. Florida DOT and AASHTO guidance focus on the redundancy in bridge design for steel bridges and not the unique design of concrete truss bridges. In summary, the AASHTO LRFD bridge design specifications, the LRFD guide specifications for the design of pedestrian bridges, and the Florida DOT Structures Design Guidelines provides limited or no guidance on the redundancy for concrete structures. NTSB staff is proposing new recommendations to AASHTO and Florida DOT, recommending that bridge design specifications include a discussion of redundancy for concrete bridge designs. This concludes staff's presentations. We are ready to answer any questions the board may have at this time.
Great. Thank you very much for those very detailed presentations. We'll take a 15-minute break. We'll come back at 10:50 according to that clock. We'll begin in about 1 minute. We are back in session. We'll begin with the questions from the board. Vice Chairman Landsberg.
Thank you, Mr. Chairman. You know, it's an observation. We've been building bridges in this country for over 200 years, and to have a failure like this is astounding. And FIGG has been very experienced. They've been building bridges for decades, and I find this, just amazing that this kind of situation could happen. Arguably, this is one of the more complicated reviews I think we've ever done. Let me start off by asking, I believe you said, has there ever been another bridge quite like this in design?
Mr. Vice Chairman, our research could not find any other bridge similar to this design.
Is concrete a suitable structure to be using in a truss bridge like this?
As I indicated in my presentation, they're generally constructed of steel in order to carry the tensile and compressive forces.
I see. You mentioned that FIGG and Louis Berger, did they modeled the loads in different phases of construction? Did I understand that correctly? And obviously the loads are going to change based on the type of support that is available during the different phases.
That's correct. FIGG modeled the completed two-span structure in its completed stage. They also modeled the main span only in different phases of construction. Louis Berger only analyzed the structure in its completed two-span structure. Louis Berger did not analyze the different various stages of construction and nodal areas.
So if I remember correctly, where the bridge was most vulnerable was in this first phase, is that correct? Because the compressive forces by the two spans would supposedly reduce the shear from one side to the other. Am I understanding that correctly?
That's correct.
Okay. One of the things that we get a lot of discussion here is about cold joints and the requirements of roughening. Was it mentioned anywhere in the release for construction plans that cold joints were to be roughened?
Go ahead.
On the build plans, the roughness was indicated to be per AASHTO, only on the pylon diaphragm connection points. There was no specific note on other areas, particularly the cold joints, and so they were to follow the FDOT specifications.
Is that a normal kind of situation in construction plans? In other words, it sounds like, at least according to FIGG, this was their submission said that this was the reason for the failure. So in the plans themselves, not referring to another document, is that normal?
If you have something that is a critical importance, it is normal to note it on your build plans.
And they didn't do that?
No, they did not. Not for this particular node location.
What percentage of the load would cold joints be expected to carry? Or what percentage of the roughening aspect? So I'm assuming you have a certain amount of weight or shear force that you have to manage. The cold joint is going to take a part of that, or the roughening is going to alleviate part of that to keep things from sliding. Any idea on the percentages?
I don't know an exact percentage off the top of my head. I will say that there are cohesion terms in calculations, and actually FIGG set their cohesion term to be 0 in order to be conservative. And so therefore, as far as we can tell, they weren't relying super heavy on the amount of roughening in their design.
Okay. I'll have other questions on oversight here shortly, Mr. Chairman. Thank you.
Thank you, Vice Chairman. Member Hamady.
First, Ms. Lamb, I do want to congratulate you on your recent award for the 29 Best Paper at the Journal of Failure Analysis and Prevention at the Material Science and Technology 2019 conference in Portland. That was on the Centerville pipeline accident. So, and I believe you got that with Dr. Mueller. So, congratulations.
Yes. Thank you, Member Hamady.
So I want to go into the last 48 hours before the collapse. That's where I want to start. First, before I do that, FHWA performed an assessment of the bridge design, and in their assessment they found that the structure provided warning before failure through development of significant and visible distress, and the structural cracking is strong evidence that the structure was progressing toward failure. So first, let me start with, and I know you stated this in your PowerPoint presentation, but what is the Florida specification or limit for cracking before it becomes a structural problem? Mr. Walsh.
In the FDOT specifications, it defines structural cracks as cracks that are deeper than 1/2 inch.
And in this case, we found that they were, at least by March 13th, they were 40 times larger than specification. I read in some of the transcripts where some of the witnesses stated that you could actually put part of your hand in it. And we have some pictures that were taken on the 13th that rulers measured in 3 different photos between 3 and 6 inches depth on these cracks. So these were not small cracks or any sort of normal cracking. These were structural problems.
That's correct, Member
Okay.
Hamady.
And so you have on March 13th, FIGG gets, and even before that, there's evidence of cracking actually going back to February 13th. But there are some photos that they receive on March 13th, and there were calls to Florida Department of Transportation stating that there wasn't a safety concern. There were calls to MCM and Bolton Perez saying there was no safety concern. Yet on the 13th, a PowerPoint presentation is developed. A meeting is set for Thursday morning at 9 a.m. A PowerPoint presentation is developed with calculations on how FIGG intends to address the cracking, and there's some immediate proposal for addressing the cracking, which was the shim under the diaphragm. At that same time, they call the structural technologies firm and ask that the re-stressing crew be available on Thursday morning. So there's a 48-hour time frame when they have this PowerPoint presentation and a number of calculations that could have been and should have been given to who at that point for review?
Well, you are correct, Member Hamady, that the issue regarding the shim plates on March 13th was recommended by FIGG as part of the Bolton Perez crack report number 3. And also later that day, it was recommended that restressing of diagonal member 11 occur.
Okay, and the intent was, per the transcript, was to go, and I'm quoting, go back one step backwards per FIGG to a previous state. Did anyone ever determine what the previous state is? And can you go back to a previous state once cracking occurs?
Very good question. It's our determination that that the main span was inelastically damaged. It was damaged through an irreversible action, which was cracking. You cannot bring a structure back to its pre-existing condition in that state.
And so a restressing was proposed, and we've determined that a restressing is a change to the design plans. Did FIGG Bridge Engineers recognize that?
No, they did not.
No. And did anyone else recognize that that was a change to the design plan, which would have triggered a peer review?
At the March 15th meeting, it was pointed out by Bolton Perez to FIGG, is a peer review going to be done on restressing number 11? The minutes indicate that FIGG concurred, but that was not done.
And I'll come back to this in a minute, but I'll just end this round for me by just pointing out that this process actually for if there's either no change to the design plan or a change to the design plan is actually laid out in the request for proposals that FIU issued, which is on page 26, section W, which is there's a process that either that the firm develops, FIGG develops a solution if there's a construction problem, and then that solution has to either go to Bolton Perez or FIU for review for 10 calendar days, which obviously didn't happen. So I'll come back actually to the more questions on this final meeting in the next round. Thank you.
Thank you, Member Comedy. I've been on this board for 13 years, and I don't think I've ever seen a case, and I guess I've deliberated, sat here and deliberated close to 200 accidents. I don't think I've ever seen one where there's more finger pointing between the parties. And you know, the finger pointing is actually correct. Everybody is pointing at everyone else. In fact, that is correct because everyone shares a piece of this accident. There were errors up and down the line committed by several different organizations and even individuals. Mr. Walsh, I was speaking to you the other day and you said something about you heard people saying something like the bridge was talking to them. What were you referring to there? What were they referring to? What was that quote?
Mr. Chairman, the bridge was talking to them specifically at the 11-12 nodal region. It was expressing alarming warning signs in the days before the collapse.
Yeah, the bridge was talking to them, but it wasn't just talking. It was screaming that there was something deathly wrong with this bridge, yet no one was listening. The cracking was 40 times greater, as we've heard, 40 times greater than the acceptable limits for cracks. But I want to clarify, Mr. Walsh, you said the Florida limits are half an inch deep, but are cracks usually not judged by their criticality based on the width? Is that what we're talking about? The limits are 0.016 inches in width. Is that correct, or is that in depth?
That's correct, Mr. Chairman. The FDOT specification does mention the structural cracks that are deeper than a half an inch. However, the American Concrete Institute recommends that generally acceptable cracking is 0.016 inches wide, which you just mentioned, and these cracks were 40 times larger than generally acceptable criteria.
And when you say that, you're referring to the width?
Correct.
Would you agree that the crack widths, being what they were, indicated severe yielding of the reinforcing steel and potentially even indicated a complete fracture of the reinforcing steel?
Absolutely.
is it true that the cracks resulted from structural loading and were unlike typical cracks that we would expect from shrinkage or just normal cracking, if you will, in concrete?
That's correct.
And would you agree that cracking of this scale in this type of structure is a clear indication that the intended load resisting mechanism were failing?
That's correct.
So in spite of that, do you remember how many times the FIGG engineer of record stated that this was not a safety concern? Do you remember?
He said this on multiple occasions. He said this during the response to the crack reports that were issued by Bolton Perez, and he indicated this at the meeting on the day of collapse on March 15th.
Yeah, I've got that PowerPoint right here, the one that Member Hamady referred to, and I count where in writing in the PowerPoint, at least on 2 occasions, he said that, and I counted up 5 times prior to that he said, according to the docket, that it was not a safety concern. And yet it's easy to sit back after the fact and say, obviously, it was a safety concern, but given that bridge was screaming, and in fact, the growth was increasing each day after that bridge was moved. Is that correct?
That's correct.
So that would indicate that it's a passive crack or an active crack?
That's an active crack.
Thank you. We'll go to the next round. Vice Chairman.
Thank you, Mr. Chairman. I'd like to just follow up a little bit here. The chairman's correct. You know, there's a lot of finger pointing going on here. All of the parties, we have FIGG, we have Louis Berger, we have MCM, we have Bolton Perez, you have Florida DOT, and you have FIU. Everybody had some level of responsibility. The process, as I understand it, is set up to make sure that not only do we check, but we double check, triple check that everything is in order so we preclude this kind of circumstance. Louis Berger was designated as the independent reviewer by FIGG. Is that correct?
That's correct.
And yet our finding, I believe it was 15, shows them that they were unqualified. How does that happen?
Louis Berger was unqualified to perform the complex bridge design or work type 4.3.1. FDOT issued a letter to Louis Berger in 2013 denying their application, citing the lack of 3 professional engineers with 5 or more years of concrete bridge design experience.
And yet somehow they showed up as qualified on FDOT's website. Is that correct?
That's correct, due to a technical error.
Oh, so mistakes were made.
Correct.
You know, one of the things that bothers me a little bit is websites that say for informational purposes only when the information is bad or misleading. So I understand that there's additional responsibility on the part of the parties to go beyond just that. But if you can't get the information correct on the website, you shouldn't put it up at all. Would you agree with that?
Yes, I would.
Okay. Louis Berger lowered their bid from $110,000 to $61,000 to become the peer review engineering firm, which is about a 43% drop by limiting their oversight scope. Is that normal in engineering circles to reduce bids to limit the scope of oversight?
You are correct, Mr. Vice Chairman, that Louis Berger did lower their bid by approximately 43%. It is incumbent upon Louis Berger to do a comprehensive review based on their lowered bid. Our recommendations address this issue, that the independent peer review firm must show their pre-qualification letter for this work type before beginning work.
So limiting the scope because you have a financial constraint basically defeats the entire purpose of having a peer review.
Again, Louis Berger did reduce their scope of work. It did contribute to the inadequate review.
Looking at the construction here, did Louis Berger or FIGG check on the bridge status during the construction phase to see what loads were being incurred? And is that something that they would normally do, or is somebody else responsible for that?
It's a very good question. Louis Berger was not part of the project during construction. FIGG personnel were located off-site. However, FIGG personnel was brought on-site during periodic intervals of the construction. For instance, during construction in the casting yard, during the move, and on the morning of the collapse.
So as the bridge was talking, screaming, as the chairman has noted, who would have been responsible for saying, hey, we got a problem here, we need to take a greater look at this, and potentially just kind of stop, particularly when you put lives at stake?
As you indicated, all parties had implied authority to close the bridge and did not act on that authority.
Could they do it unilaterally?
Yes, they could. Bolton Perez was to work collectively with FIU and FDOT in order to close the bridge, and they did not act on that authority.
Thank you.
Thank you, Vice Chairman. Member Hamady.
Well, and let's talk about who was at that meeting that morning and could have closed the bridge or recommended closing the bridge, because there was this meeting, and it was 2 people from FIGG plus 1 on the phone, 3 from MCM, 1 from FDOT, 2 from FIU, and 4 from Bolton Perez, all in the room. And this PowerPoint presentation, which the chairman mentioned and I previously mentioned, was presented with a number of calculations. Was safety addressed in that PowerPoint presentation?
Yes, it was.
And the quotes in the PowerPoint presentation were, and I'm quoting, Tuesday morning after about an hour, this is from FIGG, Tuesday morning after about an hour of review and evaluation, FIGG had conducted sufficient supplemental/independent computations to conclude that there is not any concern with safety of the span suspended over the road. Later on in the presentation, they conclude, under conclusion is, and therefore, there is no safety concern relative to the observed cracks and minor spalls, which we obviously disagree with. Did anyone at that meeting recommend shoring the structure or taking it off the piers?
Yes, they did. Bolton Perez asked that shoring be done, and FIGG responded that they did not want to do that. There was a comment by MCM, should we look into the cracking? And FIGG's response was, no, we do not want to concrete core the cracks out to determine the origin of the cracks.
And for those who might not be structural engineers, what do we mean by shoring?
It is a mechanism to the entire weight of the bridge be supported.
Right. Which had previously occurred when false work and other things were underneath the bridge, correct?
That's correct, in the casting yard.
And did anyone in the meeting ask for the PowerPoint presentation, the calculations, and the procedures for restressing that was proposed at the meeting?
Yes, they did.
It was Bolton Perez and FDOT both asked for those calculations.
Correct.
And didn't receive them. So then who had the authority in that room to call for a suspension of the retensioning?
Certainly all parties had implied authority at that meeting to suspend work and close the road underneath.
And did anyone at the meeting ask about closing the road?
No.
And in fact, there was an email that went from Bolton Perez to FDOT during the meeting, reminding them, even though both were in the room, reminding them that 2 lanes would be closed for the crane for doing the retensioning later that day, correct?
Correct.
So who knew before they showed up that there would be this retensioning? There's some indication in the documents that nobody really knew except for FIGG when they showed up at the meeting.
MCM knew, FIGG knew, Bolton Perez did not know.
Okay.
As the construction engineering inspector. This was the first time they heard about it at the meeting.
Did the grantee know, FIU?
I don't believe so.
Okay. And so, but they all had implied authority to say, we should stop, we should close the bridge.
Correct.
Which didn't happen. So I do agree with the chairman when he says this really was, and I hate to summarize, really was a failure at all levels. And it reminds me very much of our board meeting when we talked about DuPont, where everybody was involved, everybody failed, and nobody took the action that they should have taken, which was to close the road and figure out what the source of the cracking was before they did any work on it, which is the last question I have about that meeting that day. What was the restressing procedure?
The restressing procedure given by FIGG was to restress in 50 kip increments up to a maximum force of 280 kips.
So in the transcripts, they say they did, they used the ratchet on one side, they stopped. Then they went to another side and stopped, just to see what would happen, correct?
That's correct.
Okay. It's not much of a well-thought-out procedure in my view. So thanks. I will come back with additional questions.
Great, thank you very much, Member Hamady. I talked about the finger pointing, and yet at the end of the day, there will be those who are pointing fingers at the NTSB, saying we got it wrong. But when you think about it, we're the only organization involved in this that does not have a dog in the fight. Our entire existence is to get it right, not to point fingers, not to lay blame, not to assign fault, not to help the lawyers build their cases. But our purpose is to find out what happened so that we can keep it from happening again. That's why we're here. So, I want to ask you gentlemen, Mr. Walsh and Mr. Prouty, do each of you have professional engineering licenses? Qualified?
Yes, we do.
Both of you?
Correct.
Yes, sir.
And that's just a diploma mill. You just send off for that on the internet and you get that. Is that correct? No, what do you have to do to become a professional engineer?
There are several requirements to become a professional engineer. The first is to have an engineering degree. You also have to pass the the fundamentals of engineering examination, which is an all-day examination. After that, you need to accumulate work experience under another professional engineer. And to cap that off, then there's an additional professional engineering examination, which is another all-day examination.
Any idea at all what percentage of people who graduate from engineering, get an engineering degree, have a PE?
I don't know the percentage, no.
Probably not real high. Is that true?
It would depend on the discipline area.
On the discipline, yeah.
But
Well, let me ask you this: would you stake your PE reputation on the work that FHWA did Federal Highway Administration did on their calculations?
Yes, I would.
Mr. Walsh?
Absolutely.
Because when I read the party submissions, they draw serious concerns about the FHWA work. So here's something that I got from one of the parties over the weekend. It says the FHWA investigation does not use common practices for investigation of a major failure, including those previously conducted by the NTSB. It focused mainly on the design and does not evaluate the failure based on rigorous analyses and testing of the materials and the conditions at the time of the collapse. For example, FHWA did not perform any physical tests on the models of the bridge. I don't know if that's supposed to say nodes, but it says on models of the bridge connections involved in this accident. FHWA did, in fact, do materials testing of both the concrete and the rebar. Is that correct?
That is correct.
And furthermore, they talk about in here that FHWA didn't do a rigorous analysis and testing of the materials and the conditions. Their analyses were done in an office somewhere using a computer program. It was not done based on going out and exam. Well, so talk about that for a moment. Because the modeling that they did was computer modeling. Is that correct?
What FHWA performed, yes. In their check of the design, they used a modeling program as well.
Okay, so do you think does this hold any water at all to say that FHWA focuses mainly on the design? Well, that is what they focused on their modeling. Is that correct? They did focus on the design.
Yes.
And it does not evaluate failure based on rigorous analyses and testing of the materials and the conditions at the time of the collapse. Is that correct, Dr. Malloy?
So just regarding their testing they did, obviously they report on the conditions of the materials. They use the Turner-Fairbanks testing and discuss that, so they're certainly aware of the materials. They did do modeling. In fact, they did multiple people working on different models to come to the solutions they have, and they had very strong agreement between the different people working separately on this work. So it wasn't just one person doing one model. They had multiple people work on this with different approaches that came with this, very similar numbers. So we're quite confident in their work.
And how much credence do you have in would those people that perform that modeling, Dr. Malloy, would some of them have professional PE licenses?
Absolutely.
Thank you. Vice Chairman.
Thank you, Mr. Chairman. As in all cases, there seems to be a sequence of events here. Was there any damage to the bridge during the move that exceeded allowable twisting limits that might have been a source of problems?
Mr. Chairman, Vice Chairman, there was no damage to the move, no damage to the structure as part of the move. All global deformations were measured after and before the move regarding deflection, rotation, and twist. And it was found that the conditions after the move were identical to its initial state before the move.
So I don't know if these are answerable questions or not, but obviously we heard on February the 24th that when they removed some of the structure, there was a very loud crack heard, and that might be considered the beginning of all of this, and then things went from bad to worse to much worse throughout. Fair statement?
Yes, sir.
Okay. Did FIGG have any explanation on why they used the model that they did? I believe in your next to last presentation here, slide number 61, it shows a comparison of modeling results. That's a pretty profound illustration. I wonder if we could get that back up again. Thank you. So that's not just a minor error. That's a major miscalculation. Am I understanding this graph correctly?
That's correct.
How could that happen? And how could everybody miss it? Two questions.
FIGG's design error, this was a design error that FIGG did. It led to a significant underestimation of demand and overestimation of capacity. It's unexplained why FIGG used and exclusively used the results from the main span fixed support and simple support models. Had FIGG used the results from the completed two-span structure, those results would have been in line with FHWA's post-collapse check.
So no reason given then, other than it seemed like a good idea at the time.
It's unexplained.
No further questions, Mr. Chairman.
Thank you, Vice Chairman. Member Hamady.
What was the Florida Department of Transportation's role here?
Florida DOT's role in this project was to certify the local agency, which was in this case FIU. Additionally, their role was a pass-through of the federal Tiger grant funds to FIU.
And under federal regulations, it states, the State Department of Transportation has the responsibility for construction of all federal aid projects and is not relieved of such responsibility by authorizing performance of the work by a local public agency, in this case FIU. The State Department of Transportation shall be responsible for ensuring that such projects receive adequate supervision and inspection to ensure that projects are completed in conformance with approved plans and specifications. They did approve the plans and the specifications at some point after it was stamped and sealed by the engineer, submitted by FIU, and certified by Louis Berger, correct?
Correct.
Over the last 5 years, 2013 to 2018, how many transportation infrastructure projects has Florida Department of Transportation managed?
I don't have an exact number.
It's 2,304 projects, 1,801 design, build, and conventional projects, and 493 lap projects. Do you know how many lap projects were pedestrian bridges in Florida?
3.
3. And how many of those were non-redundant and of unique design?
None had a single load path non-redundant design.
And in fact, you couldn't find one of similar design when you looked worldwide, correct?
That's correct.
And so let's talk for a second about FIU's role. Under federal regulations, FIU had responsible charge of the project. What does that mean?
Responsible project, FIU's Associate Vice President of Facilities Management was responsible for detecting any workmanship or materials that were defective and to bring that to the attention of MCM.
And was FIU aware of the cracking?
Yes, they were.
How many lap projects had FIU managed before this?
None that we're aware of.
And would you consider this a low-risk project or a high-risk project?
We would
And
consider
why?
We would consider it a high-risk project because of its complex bridge design features.
So do you think it's appropriate that a school, granted an extremely good school, would have responsible charge of a major complex concrete project over a state-owned roadway that was high risk, with essentially Florida Department of Transportation being essentially hands-off because they never went? They never had an inspector on site.
We would agree with that, Member Hominy.
Yeah. So to me, FDOT has greater expertise. So do you think FDOT provided appropriate oversight over this project?
Certainly through the LAP agreement, they were not required to have an inspector on site through the LAP agreement. I think our recommendations address this issue, that FDOT should have more authority on these types of projects and certainly should have inspectors on this type of project.
Dr. Malloy, do you think they provided appropriate oversight?
So with regard to the FDOT oversight, there were multiple places where they were providing oversight. They had comments on the plans. Unfortunately, they labeled those informational only, and so there wasn't really any action on that. And they did detect that the project wasn't being peer reviewed by an external, but they failed to detect that it wasn't done by a qualified firm. So they certainly were involved in the process. I think a greater involvement by them would have improved or lessened the risk.
Agreed. And so and just two more questions, under the Florida Administrative Code, FDOT must evaluate the performance of consultants on professional services contracts, such as FIU. There are different performance ratings from 5 to 1, from outstanding performance to unacceptable performance. Was FIU given a performance evaluation rating after the collapse on March 15th?
No, they weren't.
And did FDOT say why?
Yes, they did. They said pending the outcome of the NTSB investigation.
Was FIU's LAP certification evaluated after the collapse?
No, it was not.
And what did FDOT say to that?
FDOT said that they were not going to do a performance evaluation of FIU as a local agency pending the outcome of the NTSB investigation.
Thank you.
Thank you, Member Hamady. Well, we've been in here for 2 hours, and so I want to make sure that I understand what happened here. The way I understand it, there are basically 3 main errors that led to the bridge collapse and the catastrophic loss of life. And I want you to see if I've got this right. First, the bridge was under-designed. And when I say it was under-designed, I mean that FIGG underestimated the demand or the load on the bridge, and they overestimated the capacity, meaning the strength of the bridge. Am I correct on that bullet point?
That's correct.
So those errors, the next point, error in this chain, is that error should have been trapped through an independent peer review. But as it turns out, the independent peer review was inadequate and did not catch those design errors. Is that correct?
That's correct.
And if that was done properly, that would have caught caught FIGG's error before the bridge was built.
Correct.
And finally, once those errors were in place, or that design error was in place and not trapped, those involved in the project did not recognize or appreciate the criticality of those errors and therefore did not make the decision to close the bridge for people on it and traffic underneath it. Is that correct?
Correct.
Thank you. So a very complex situation, but it really boils down to those 3 points. Now, if we could pull up slide number 59, please. So we looked at this when I met with staff again yesterday afternoon, and as I understand it, these are 4 models that FIGG used, but they did not use the most conservative one in designing the bridge. So, Mr. Walsh, Mr. Prouty, if you could explain to us what we're talking about here, what this error was.
Mr. Chairman, FIGG exclusively used the main span simple support and fixed support models that are shown on the lower half of the screen for the design of every nodal region on the main span. Had FIGG used the results from the completed two-span model, which is in the upper left-hand corner of the screen, those results would have been in line with FHWA's post-collapse check.
So they basically used a model that was not conservative in creating their calculations.
Correct.
Yet I'm reading in something that I think was produced by FIGG and sent over the weekend. It says FHWA submission to the NTSB. Let's see, in FHWA's submission to the NTSB of its evaluation of the submitted design calculations notes it is not an evaluation of the final bridge design and therefore is not useful in determining the cause of the accident. In fact, it was FIGG that used the wrong model. Am I confused on this?
No, you're not.
So FIGG is apparently casting a stone at the FHWA, saying that they did not evaluate the final bridge design. The final bridge design, in fact, was the one that FIGG should have used.
That's correct.
Wow.
And just for clarification, sir, Mr. Chairman, there is a comment that is made that the release for construction plans were not where the analysis was done. We were doing the analysis on the design plans. However, it's the design plans that lead to the plans that are in the release for construction. And those design plans led to the under-design of this nodal region. So, you know, they're related. They're not completely independent.
Thank you. Vice Chairman, Member Hamady.
In the report, you note a number of other node regions where FIGG severely underestimated demand and significantly overestimated capacity or the ability to resist that demand. I think it's 1, 2, 2, 3, 4, 5, and 11, 12. Yep, and close on 10, 11. Is that correct?
That's correct.
And so, in fact, 11, 12, and you have some calculations here, but it looked like the demand was even greater at 1, 2. So my first question is, do you believe this bridge would have failed eventually at 1, 2?
It's a very good question. The 1, 2, or the south end of the main span had unintended capacity because its diaphragm was 42 inches wide compared to the pylon pier diaphragm that was 24 inches wide.
And it's interesting because I didn't realize that until we obviously received the draft report, but then in looking at the model, you can tell that on the south pier, it's much more expansive than the pylon pier, and that's because why? They viewed it as unfinished at that point, correct? The pylon pier side, because of the backspan wasn't on yet.
That's correct.
And so what was the difference in the construction from the south pier to the pylon pier at the time of the collapse? What were the differences there?
In terms of the diaphragm widths, again, they were 42 inches versus 24 inches wide. The depth of member 2 was 36 inches in depth versus member 11 that was 24 inches wide. And as stated in Mr. Prouty's presentation, the backspan was going to be constructed. So that was the next step in the process.
Which would have helped resist some
correct.
of that shear force. Now, on the south pier, you had another structure sort of abutting it, which was this, I believe there were steps, there was some sort of, which may have failed at some point, but there was some sort of structure there.
It acted more like a bridge abutment, but also had the future steps and elevators that were going to be there for the students to use. But that end of the bridge was more like a bridge abutment where it had a seat that end of the bridge sat in. So it gave it additional resistance, whereas the north end did not have that additional resistance.
Okay. And so, really quickly, I did want to go back to the roughening just for a second. Why is that important?
The roughening is important because it can give additional capacity if it's specified and then used in the design and performed.
Okay, and we talked about the construction plans where not every node was called upon for roughening. Only some of them were. We don't know why that was, correct?
That's correct.
And do you know, there are some assertions that that was the cause of the cracking. We don't believe that. So can you talk about why we don't believe that?
Calculations were performed that altered the cohesion terms and the load factors used to give the highest capacity possible, essentially giving the highest benefit of the doubt to the design, and even allowing for things that the AASHTO LRFD does not allow for, counting capacity that they wouldn't count, even doing that. It was not enough capacity to overcome the demand that the bridge needed.
So you believe that the collapse would have occurred regardless?
Yes.
Okay. What should have been done to correct some of these errors? Mr. Walsh, Mr. Aceta, Dr. Malloy?
I mean, the tragic part of this collapse is that some of the things were in place to correct these errors. An adequate peer review would have caught that design error. I mean, people make design errors at times. We're people, we make mistakes. An adequate peer review should have caught that and then should have allowed for a redesign. As the chairman stated too, as the cracks were progressing, people were watching those cracks, people were concerned, they were noting it and reporting it to various groups. They could have taken action then, but they failed to take the action. So those are two places in which that design error could have been caught and this tragedy could have been prevented.
Thank you.
So that was a general answer, Dr. Malloy, but what could have made the design more robust? Would increasing the footprint of member 11 worked to give more space for rebar?
As one of the things that FDOT did point out, and FHWA also pointed out that additional concrete was needed at that node, but then again, it was only taken as an advisory statement. But in essence, the calculations also underestimated the amount of steel in that shear plane. So it did not have sufficient steel to help resist the shear.
Great, so let's talk about that. Member 11 only had 4.8 square inches in the cross-sectional area of rebar. In order to sufficiently provide the shear resistance, how much more rebar would it have needed?
If the demand was calculated correctly, and if the capacity was calculated correctly, it would have needed 18 square inches of steel reinforcement.
And so, people have heard me say this before, there is no such thing for me as simple math. But the difference between the 18 and the 4.8, that's a 300% deficit, 300% difference in the amount of rebar that was there in the amount that it would have required to provide the proper shear resistance.
That's correct.
Was this, if member 1112 joint, was it constructed or designed in accordance with the AASHTO LRFD bridge design specifications?
It was designed per AASHTO, but the construction plans called for the Florida DOT specifications to be used.
Now, what does that mean?
The AASHTO recommendation is that any surface that is intentionally roughened be done to a 0.25-inch amplitude. However, the Florida DOT does not specify a number at all. It just generally says that it should be clean and free of loose debris.
So it was designed to AASHTO but built to FDOT standards?
That's correct.
Okay, thank you. And back to what Member Homendy just said, even if we had the surface roughening as called for in AASHTO, meaning 1/4 of an inch amplitude, even had that been there in the cold joints, based on the design issues of underestimating the load and overstating the capacity of the bridge, this bridge still would have collapsed.
That is most likely true, yes.
Now, the question I have is, this is a picture of, this looks like a picture of the forms, the deck. So when I saw that picture, I was a little bit surprised. I thought, because it looks like the forms are already in place for the trusses before the deck of the bridge is even poured. It would seem to me that you would pour the deck, and how do you roughen the joints if the forms are already covering up those areas that would become cold joints?
Well, there were different staging, and they had to have some formwork in place to be able to have all the rebar that was required to be tied in from the deck through the truss members to the canopy. But there was very little room to do any roughening once the deck was poured, before they poured anything for the truss members. So there wasn't very much room to do any type of roughening.
Okay, because you'd have to get up under here after the deck concrete was already poured and roughen it.
Yes.
But the forms are in the way. But I guess they can work around that. But in fact, we know that they did not roughen it.
Correct.
But we also think, from what I've heard, is the notion that the surface was not roughened is somewhat of a red herring. Because of the bridge under design, it still would have collapsed.
That and the fact that what the photograph you're looking at still has the truss members exposed. So they would have poured the deck. You have the rebar in place for the truss members. It's still exposed, but as I said, because of the amount of rebar, it would be difficult to go in and roughen that surface. But that surface, unlike the deck, was unfinished. They finished the surface, the portion that would be walked on. So that area that's in the footprint underneath each one of those members, the truss members, it wasn't roughened intentionally to the LRFD standards of 1/4 of an inch, but it was not finished, so it still had a rough surface.
And if I may, you are correct. From the work we did, had they roughened it, it would not have made a difference in this case. So the fact that it was roughened or wasn't roughened is not really critical, because it wouldn't have changed the outcome.
Thank you. Member Homendy.
I want to go back and talk about the move a little bit, because there's been a lot of discussion about the move, at least by one of the party members that came in to meet us and submit comments. So I do want to talk about that. There was a limit placed on twist during the move or rotation that was plus or minus 0.5 degrees, I believe. Who was at the move? Who was present outside of outside of Barnhart, which was the mover, and the crane operator? Who would have been present there?
MCM and FIGG was present during the move.
And so, by my count, 1, 2, 3, 4, 5. So 6 FIGG personnel were present at the move, and there were sensors that were placed on the transporters. I think there was one on the center line, and then 2, one on each of the transporters during the move, so they could do real-time monitoring to determine if twist was exceeded.
That's correct.
And was it exceeded?
Yes, it was.
Twice, correct?
Yes, it slightly exceeded twice.
And was the move shut down? Was there an all-stop at that point during the move to look at the structure?
Yes, there was. The second incident, where it was slightly exceeded to 0.75 degrees, there was an all-stop issued due to the main span coming in contact with the bearing pads on the south pier. It was all stopped, and the twist was brought back into specifications.
And were there engineers on site that looked at the span once it was in place on the diaphragm, on the piers?
Yes.
Did they find anything unusual?
No.
Did anyone in your interviews, whether it was FIGG or anybody else, state that the move was unusual in any way?
No, they did not.
And was there, I guess they finished the move at about noon, 12:30? Is that right, on that Saturday?
Correct.
And so did the entities look at, on top of the deck, did they look at everything and then under the diaphragm?
A FIGG employee did take photographs of the existing cracking that had occurred prior to the move, and it was documented that there was no growth of cracks during the move.
And so there is an assertion that the exceedance in the twist twice during the move may have caused the collapse, ultimately. We don't agree with that, and can you tell me why?
We don't agree with that because of global deformations were measured on the main span. That included rotation, twist, and deflection. They were measured after the move and before the move, and the conditions after the move were nearly identical to its initial state.
Thank you.
Thank you. I know that there'll be questions about accelerated bridge construction. Did this investigation reveal any inherent problems with ABC in itself?
No, it did not.
Thank you. I just want to confirm something. Did you say in one of your presentations that FIGG had determined that this bridge was redundant, whereas we found that it was non-redundant?
That's correct, Mr. Chairman.
And because they assumed that it was redundant, did they use a different calculation than they would have if they would have assumed that it was non-redundant?
If they assumed that it was non-redundant, they would have used a redundant factor of 1.05, which is in the AASHTO LRFD bridge design specifications. However, they believed it was redundant and used a redundancy factor of 1.0.
In the end, would that have made a difference?
No, it would not have.
But it still shows the inaccuracy of their calculations
Correct.
and their assumptions.
Correct.
Do you believe that when you're designing a bridge that attention to detail is important?
Yes, sir.
Do you recall what day the bridge was moved? The date?
March 10th.
March 10th. And I just noticed that in the PowerPoint presentation that FIGG gave on the morning of the collapse, somebody had put it was moved on March the 11th. So it was moved on the 10th, but yet FIGG says it's the 11th. So I'm talking about attention to detail. If you were to come in and give the NTSB a presentation about your company, and you wanted to state that you built a bridge in the country of Colombia, how would you spell Colombia? Would you spell it Columbia, or would you use an alternative spelling? Colombia. Attention to detail matters. Is that correct?
Correct.
Thank you. I revert to you.
I did have some questions about the independent review. I wanted to circle back a little bit on whose responsibility it is to ensure independent peer reviewers are pre-qualified. And I'm trying to figure out what should have happened in this case. In this case, FDOT had not given, had not designated Louis Berger as a complex concrete bridge design. They were not pre-qualified for that. They did not have a pre-qualification for letter for that, but they listed them on the website at one point. Is it possible that other entities might be on that website, listed on that website, or did FDOT do a review?
FDOT did a review and corrected that error.
Was there anything at the time that said the listing was informational only?
I don't believe so.
And is it normal that a design firm would go to the website and use that listing, or would they ask for a pre-qualification letter? What is the, I didn't see a requirement that they had to get a pre-qualification letter, but is it normal that that's what you would do? Is that standard practice?
We feel that FIGG's due diligence should have required that Louis Berger submit a pre-qualification letter indicating that they were qualified to do this work.
And so at some point, this Louis Berger does this independent review. The construction plans are sent to FIU. They're signed and sealed by FIGG's professional engineer. FIU stamps it, release for construction, then sends it to FDOT for approval, correct?
No, the release for construction plans are signed and sealed by the FIGG engineer of record.
And then they're submitted directly to who? FDOT or FIU?
In this case, they were submitted to FIU as the owner.
Correct. And that's what I mean.
Okay.
And then FIU submits that to FDOT.
Correct.
Okay. So FDOT then reviews the plans, provides comments, correct?
Correct.
Did FDOT look to see if Louis Berger was qualified, since they're the agency that does the pre-qualification?
Certainly our recommendations address this issue, Member Hamady, again, that any independent peer review firm must submit their pre-qualification letter. for this work type before beginning work.
So in this case, a independent peer review was done on the entire structure. I read the transcript where we interviewed the engineer from Louis Berger. They said they looked at the entire structure, not components of the structure, and certainly not the modes, that would have exceeded the budget and the time allowance. Now, that's one thing I want to talk about, because at some point, and I saw this in some of the documents, FIGG had decided that some other office in FIGG could do the independent peer review, correct?
Correct.
Which wasn't really independent.
Correct.
So did that time period where they had counted on this other office within FIGG to do the independent peer review, did that cut into the time? Is that why the time was lessened from 10 weeks to 7 weeks?
Yes, it did.
Okay, so what should have an independent peer review look like in this case? And how, I mean, he seemed to indicate that, well, I didn't have enough time to do it. It would have required, a greater scope of work. It's something I raised with FIGG. It wasn't ultimately agreed to. So what should have an independent peer review look like?
So an independent peer review should have been at the very beginning, a separate firm other than the engineer of design to conduct a comprehensive independent peer review of the engineering plans that includes the various stages of construction and nodal areas at the onset.
Great. I may have further questions, but go ahead. No.
So regarding the independent peer review, what is it that led FIGG to believe that they could have done this in their own firm using a separate division? Because I read the contract and I read the request for proposal, the RFP, from FIU to solicit bids, proposals for the construction, which MCM ultimately got. That was very clear about it needed to be an independent review. But what is it that made FIGG believe initially that they could do it in-house?
We feel that what's in the plan preparation manual of FDOT specification is clear. The independent peer review is an independent firm that conducts this review that has no other involvement in this project. We have do not know why FIGG thought that they could use the independent peer review within their own firm. It contributed to the delay. It contributed to the inadequate review, and our recommendations address this issue.
Okay, I came back. Yeah, it's kind of funny because FIGG would when they came in to talk to us individually, they pointed out that when they were talking about surface roughening, they said, oh, well, the plan preparation manual is the Bible. So that sort of supersedes everything. But yet, when it came to this issue of the independent peer review, it very, very clearly spells it out in the plan preparations manual, just as you said. The peer review, it talks about it has to be independent verification, using, all kinds of different things. So, but it's clear here. In the plans preparation manual is an FDOT manual.
Correct.
Yeah. It was FDOT ultimately who caught the fact that FIGG was trying to do this in-house.
That's correct.
When Louis Berger initially took on the work to do this independent peer review, and they came up, no, I'm sorry, when they initially bid it at $110,000, they were planning to do the full enchilada, the bridge and the various stages of the construction, the various 3 stages, and check each node. Is that correct?
That's correct.
But then when they reduced their bid to 61 or 63, 61,000, did they alert FIGG that they were going to truncate their services other than the time frame?
There was some correspondence regarding that, Mr. Chairman, regarding Louis Berger said it indicated a reduced fee associated with reduction of scope. But again, it's incumbent upon Louis Berger to do a comprehensive review based on a lower bid.
Thank you. So who has responsible charge for this project? Member Hamady used that term, responsible charge. And I see potentially 2 people, so 2 organizations. Who has responsible charge?
In terms of the construction of the project, MCM has responsible charge until the project is completed. And Member Hamady is correct regarding FDOT's supervision responsibility. They are not relieved of their supervision responsibility as part of the local agency agreement.
Now, I'm looking at page 88 of the draft report. It says 23 CFR 655.105 requires the LAP to have responsible charge, to basically oversee the day-to-day operation, including safety issues. The LAP in this case is FIU. Is that right?
That's correct. It's the contract between local agency agreement between FIU and FDOT.
So FIU, all right, so so FIU has responsible charge, or is it MCM?
Again, during construction of the project, MCM would have control of the project until the project's completed, and then FIU would be responsibly charged after it is completed.
I see, thanks. Now, I'm looking at a different page in the document, page 83, and it says the Florida Administrative Code talks about, it says responsible charge means the degree to which the control an engineer is required to maintain in engineering decisions. And the engineer is in responsible charge is the engineer of record, and that would be FIGG's employee.
That's correct. I mean, during construction, the engineer of record, according to Florida Administrative Code, just like you had indicated, Mr. Chairman, the engineer of record is responsible for the safety and welfare of the public.
Thank you, Member Hamady.
Well, I only partially agree with that, because under the law, under the regulations, everybody is responsible for public safety. That's FDOT, FIU as the grantee, and everybody that FIU contracted and subcontracted with, correct?
Correct.
So ultimately, you have, at each stage, everyone had some sort of responsibility for public safety, which was, at some point, everybody just didn't
Correct.
focus on safety.
That's correct.
In fact, that's in the law, that they have to focus on the health and safety of the public and
Right.
the workers working around the bridge.
Exactly.
Okay. Oh, no further.
Is it true that up to the point, including this March 15th, 9 a.m. Meeting that was held, that most of the concern with FIGG was in the diaphragm and not in the member 11 and 12 nodal region?
I think the crack report number 3 that was issued by Bolton Perez to MCM requesting FIGG's response, there were photos in that crack report showing cracks on the diaphragm, and there were also photos showing cracks at the nodal 11-12 region.
Thank you very much. I want to talk about, finally, the last straw. I mentioned 3 bullet points. The bridge was under design. That error was not trapped by an adequate peer review, and finally, the decisions or the lack of decisions to close the road. Who had the authority and responsibility to close the bridge? To close the road?
I think as we discussed, all parties had that implied authority, Mr. Chairman.
I was questioning in my mind whether or not FIU really had that responsibility. They came in and they hired Bolton Perez to really sort of be their agent to make sure the construction was being done properly. But Sean and I were talking about this yesterday. You can contract out your authority, but you can't contract out your responsibility.
Correct.
So FIU also had a role in potentially making the decision to close the road. They had that responsibility.
Absolutely, Mr. Chairman. They were on the bridge before the morning meeting at 9 o'clock taking photos of the cracking. And they had authority through their Associate Vice President of Facilities Management to detect defects in workmanship and material and bring that to the attention of MCM.
Thank you. Are there any further questions?
What is, and this is an easy one, Dr. Malloy, what's our responsibility in this safety investigation?
So our responsibility in the safety investigation is to determine why this happened and come up with solutions to prevent this from happening again.
And part of our mission is transparency in the process.
That is correct.
I think throughout this, ever since the collapse, there have been questions about transparency in the process. And just like any investigation, we can release documents when we can release them. But we did take the step of opening the docket on what day?
We opened the docket on October 8th.
So we opened and why did we make that decision?
We typically will make the decision that it's going to be opened before the board meeting. When all the materials are ready, we make that decision to open. In this case, we were ready to open 2 weeks before the meeting.
And there's a lot of materials, and we've gone through all the materials in the docket, and we've allowed the public to have access to that material so they can see what we see and what we've found, which I think is important. So I debated whether I wanted to even bring this up, but I'm going to because I think there were failures at all levels. So I was extremely disappointed and shocked that we received a letter on October 7th from FIU, Bolton Perez, FIGG, MCM, and Structural Technologies. Are you aware of, I'm sure you're aware of the letter, Dr. Malloy, from October 7th?
I am aware of that letter, yes.
So that letter requests that we delay opening the docket because they believe doing so may have negative consequences in connection with achieving a full and final settlement in the ongoing settlement negotiations and the underlying litigation arising from the bridge collapse, and it could reduce the benefits to the families and other claimants by prolonging settlement for years. I find this shocking and disappointing, frankly. And I don't mean to take away from the safety issues that we are talking about today, but I think it's our job to point out when something that I believe, a request that's totally inappropriate, comes our way. Of course, we denied that request. Mr. Malloy, or Dr. Malloy, how long have you worked at the NTSB?
25 years.
Have you ever received such a request?
No, I have not.
Was there a somewhat similar request in this investigation at any point?
So we informed the parties that we were going to be doing an investigative update, again, in trying to keep with our values of transparency, providing new information as we were going through the investigation. Prior to issuing investigative update number 2, we were asked if we could change the date for the release to not affect outcomes in the civil proceedings.
And I think it's important to once again state our job is not to weigh in on litigation or civil proceedings. Our job is safety and to protect the public and to ensure that and move forward recommendations to prevent a similar accident from occurring again. I think this is, again, completely inappropriate, and I highlight it. This letter is in our docket, and I considered not highlighting it, but I think we should highlight it because it's not a request that should come our way again. Thank you.
Dr. Malloy, who was it that asked us to delay the opening of the November update?
It was a letter sent to us by 5 of the party.
No,
I'm sorry.
you're talking about...
Oh, the November update.
November update.
That was FIGG.
Thank you. Are we ready to move to the findings? Ms. Bryson, if you'd please read the proposed findings.
Yes, sir. As a result of this investigation, staff proposes 30 findings. Number 1, the emergency response by local fire departments and law enforcement personnel was timely and adequate. Number 2, the concrete and steel materials used during construction of the pedestrian bridge were not a factor in its collapse. Number 3, the hydraulic jack used to post-tension the steel rods to member 11 was operating as expected at the time of the bridge collapse. Finding number 4, there are 3 parts to it. So in finding number 4, number 1, the FIGG Bridge Engineers bridge design was non-redundant because it provided only a singular load path. 2, FIGG used poor judgment when it determined the bridge was a redundant structure. And 3, FIGG erroneously used a redundancy factor of 1.0, which is commonly used for structures with redundant load paths. Number 5, even with surface roughening to a 0.25-inch amplitude performed at node 1112, as called for in other sections of the FIGG Bridge Engineers plans, this surface preparation would not have sufficiently increased the structure's capacity to counteract the demand load for interface shear, and the bridge would still have been under-designed and could have failed. Number 6, the FIGG Bridge Engineers construction plans inconsistently identified when intentionally roughened surfaces were needed to fulfill the assumptions of the bridge design. Number 7, because FIGG Bridge Engineers, 1, did not use the lower bound load factor for determining the governing of net compression, which is P sub C, in the interface shear, and 2, incorrectly increased and amplified the effects of the clamping forces across the interface shear surface, its bridge design calculations resulted in a significant overestimation of capacity. Number 8, FIGG Bridge Engineers, number 1, made significant design errors in the determination of loads, leading to a severe underestimation of the demands placed on critical portions of the pedestrian bridge. and 2, significantly overestimated the capacity of member 1, 2, and 11, 12 nodal regions. Number 9, based on analytical modeling results, FIGG Bridge Engineers should have considered the loadings from all critical construction stages when designing the pedestrian bridge and determining the governing interface shear demands. Number 10, in several instances throughout the bridge design process, the FIGG Bridge Engineers models produced reasonable estimations for interface shear demand, and these values were not always used in the design of truss members to resist force demands. Number 11, FIGG Bridge Engineers analytical modeling for the bridge design resulted in a significant underestimation of demand at critical and highly loaded nodal regions. Number 12, the concrete distress initially observed in nodal region 11-12 is consistent with the underestimation of interface shear demand and the overestimation of identified capacity in the bridge design. Number 13, the FIGG Bridge Engineers' design of the rebar placement in node 11-12 resulted in less reinforcing steel being available and diminished resistance to the critical interface shear demand, which contributed to the collapse of the bridge. Number 14, the member 11-12 nodal region contained non-structural voids, parentheses, 4 hollow vertical pipe sleeves, within the concrete that made it less able to resist applied loads, which contributed to the destabilization of this node through overstress and the subsequent collapse of the main span. Number 15, although it may be generally accepted that concrete itself is susceptible to cracking, the rate of premature concrete distress was clear evidence that the structure was progressing towards failure and should have alerted FIGG Bridge Engineers and MCM to the origin of the distress mechanism that was causing the cracking and the rapidity of cracking progression. Number 16, Louis Berger was not qualified by the Florida Department of Transportation to conduct an independent peer review and failed to perform an adequate review of the FIGG Bridge Engineers' design plans and to recognize the significant underdesign of the steel reinforcement within the 11-12 node, which was unable to resist the horizontal shear between diagonal 11 and the bridge deck. Number 17, FIGG Bridge Engineers' failure to adhere to the Florida Department of Transportation plans preparation manual requirements for a complex Category 2 bridge structure within its work proposal to MCM, calling for an independent firm to conduct a comprehensive peer review, led to the inadequate peer review performed by Louis Berger, which failed to detect the underdesign of the bridge. Number 18, had the Florida Department of Transportation plans preparation manual called for all nodal forces of Category 2 bridge structures to be checked and verified by a qualified independent peer review, this collapse might have been prevented. Number 19, as part of its oversight of local agency program projects and new construction, the Florida Department of Transportation should have verified Louis Berger's qualifications as an independent peer review firm for complex bridge design concrete upon receiving the 100% certification letters for the bridge foundation, substructure, and superstructure plans. Number 20, FIGG Bridge Engineers did not perform its due diligence when it contracted with Louis Berger for the independent peer review of this highly complex and uncommon concrete bridge design. Number 21, the restressing of member 11 was a manipulation of loads that constituted a change to the FIGG Bridge Engineers' design and, before being implemented, should have been independently peer-reviewed and signed and sealed by a professional engineer. Number 22, the structural cracking and northward dislocation of the upper part of the member 11-12 nodal region, as documented in the days leading up to the collapse, was strong evidence that the structure was progressing towards failure, and the Detensioning of the post-tensioning rods located in member 11 significantly increased the damage to the member 11-12 nodal region. Number 23, although the FIGG Bridge Engineers, engineer of record, and design manager were engaged by MCM to assess the increased cracking of the structure, they neither recognized that the singular load path in this non-redundant bridge had been compromised, nor took appropriate action to mitigate the risk of failure. Number 24, beginning with the cracking identified on February 24th, 2018, the distress in the main span structure was active, continued to grow, and was well documented by all parties involved in the design, construction, and oversight of the bridge. 25, neither Florida International University, MCM, FIGG Bridge Engineers, nor Bolton Perez and Associates Consulting Engineers took the responsibility for declaring that the cracks were beyond any level of acceptability and did not meet Florida Department of Transportation standards. Number 26, under the terms and conditions of the contract, Bolton Perez and Associates Consulting Engineers had the authority to direct or authorize partial or complete road closures as necessary, acting in concert with the Florida Department of Transportation and Florida International University. However, none acted to close the road under the bridge, contributing to the severity of the impact of the bridge collapse. Number 27, local agency program agreements require stronger language to clarify that the certified local agency has the authority to immediately close a bridge when structural cracks are first detected or in situations that require further investigation to protect the health, safety, and welfare of the public. Number 28, given the pedestrian bridge's unique, non-redundant design, the Florida Department of Transportation should have ensured that the local agencies involved in the project had adequate staff who were trained and experienced in administering these types of uncommon bridge designs. Number 29, complex local agency program projects involving non-redundant bridge designs would benefit from greater Florida Department of Transportation involvement. And number 30, given the serious consequences of the error made by FIGG Bridge Engineers in assuming that the bridge had a redundant design when in fact it did not, and the current lack of guidance concerning redundancy design in concrete and pedestrian bridges, design specification publications for concrete and pedestrian bridges should be revised to include redundancy guidance.
Thank you very much, Ms. Bryson. As far as amendments, I have one that I'll propose. I believe Member Amity has one as well. So if it's okay with you, we'll just go in the order in which they are. Yours is for 29. Great. Okay. So I'd like to offer an amendment. This is what was emailed to you last night. And I was just looking for yesterday afternoon, this was emailed to you, and you have a copy of it here. And so you can see the revisions and strikeouts. So my motion is to amend finding number 5 to read as follows. Even if the cold joint surface of nodal region 11/12 had been roughened to a 0.25 inch amplitude, node 11/12 would not have had sufficient capacity to counteract the demand load for interface shear, and the bridge would still have been under-designed and could have failed. That is my motion. Is there a second? The Vice Chairman has seconded it. As far as discussion, I believe that the way that it is currently written, it could potentially imply, the way it is currently written, it says even with the surface roughened to a 0.25 inch amplitude. Well, that could be read to imply that it was roughened to a 1/4 inch amplitude. So I was just trying to clean up the language a little bit to say that even if it had been roughened, And so that's the gist of my motion. Further discussion, questions? Staff, do you have comments?
Mr. Chairman, the staff supports the proposed change.
Okay, it's been moved and seconded. There's no further discussion that I can see. All in favor of adopting finding number 5 as amended, please signal with a hand and say aye. Opposed, there are none. The finding number 5 has passed unanimously. Member Hamidi, I recognize you.
Yes, I offer a motion to strike finding number 29 and replace it with the following language. The Florida Department of Transportation should have provided greater oversight of this complex local agency program project to ensure that all safety issues were identified and addressed.
Okay, that's your motion. Is there a second? The Vice Chairman has seconded it. Discussion, please.
Yeah, on the existing number 29 finding, it is very limited to non-redundant bridge designs, which I understand this was a non-redundant bridge design, but we weren't able to find a similar bridge design worldwide. And in Florida, you have 2,300 total projects with the Florida Department of Transportation, 493 of which were LAP, 3 of which were LAP pedestrian bridges. None of them were non-redundant designs. So I felt it was a bit limiting, so I wanted to be a little bit more expansive and highlight the role of the Florida Department of Transportation, which I think is consistent with our recommendations, which will be later considered.
Thank you very much. Further discussion? Staff.
Mr. Chairman, staff supports this change also.
Okay, it's been moved and seconded with no further discussion to adopt the finding as proposed by Member Hamidi. All in favor, please signal with a hand and say aye. Opposed? The motion to pass her finding has been approved unanimously. Now, I'm under the impression that staff might have something for the board's consideration.
Mr. Chairman, we do have something for your consideration. After the draft report was delivered to board members, staff identified a change that they would like to make to finding 14 to include some text that we inadvertently left out. The proposed change would be the member 1112 nodal region contained non-structural voids, 4 hollow vertical pipe sleeves, and the horizontal drain pipe, that was in parenthetical, within the concrete that made it less able to resist applied loads, which contributed to the destabilization of this node through overstress and the subsequent collapse of the main span. And we ask the board to consider that.
Well, the board chairman will entertain a motion to adopt that finding.
So moved.
Vice Chairman has moved, and Member Hamidi has seconded to adopt that as a replacement finding, 14. Is there any discussion?
Again, both of these elements are important in discussing the factors in that region that affected the lack of support in the concrete. So we just think it makes for a more complete finding.
Very good. And so really the part that you've added there is the word "and the horizontal drain pipe."
That's correct.
Okay. Any further discussion? All in favor of revising finding number 5 as moved and seconded, please signal with a hand and say aye. Opposed? Finding number 14 has been revised and passed unanimously. Now let's go back and are there any other amendments to the findings? So now we need to go back and adopt the findings as amended. Do I have a motion to adopt the findings as just amended?
So moved.
Vice Chairman has moved it. The member Hamidi has seconded it. Is there any discussion on the findings? There's none. All in favor of adopting the findings as revised, please signal with a hand and say aye. The findings have been unanimously adopted as revised. Ms. Bryson, if you'd please read the proposed probable cause.
Yes, sir. Staff proposes the following probable cause. The National Transportation Safety Board determines that the probable cause of the Florida International University, FIU, pedestrian bridge collapse was the load and capacity calculation errors made by FIGG Bridge Engineers, Inc. in its design of the main span truss member 1112 nodal region and connection to the bridge deck. Contributing to the collapse was the inadequate peer review performed by Louis Berger, which failed to detect the calculation errors in the bridge design. Further contributing to the collapse was the failure of FIGG engineer of record to identify the significance of the structural cracking observed in this node before the collapse and to obtain an independent peer review of the remedial plan to address the cracking. Contributing to the severity of the collapse outcome was the failure of MCM, FIGG, Bolton Perez and Associates consulting engineers, FIU, and the Florida Department of Transportation to cease bridge work when the structure cracking reached unacceptable levels and to take appropriate action to close Southwest 8th Street as necessary to protect public safety.
Thank you, Ms. Bryson. Is there a motion to adopt the probable cause as presented? Member Hamady has moved, and the Vice Chairman has seconded. Any discussion? Seeing none, all in favor of adopting the probable cause as presented, please signal with a hand and say aye. Opposed? There are none. The probable cause has been adopted unanimously. Now, Ms. Bryson, if you'd please read the proposed recommendations.
As a result of this investigation, the National Transportation Safety Board makes the following 11 new recommendations. To the Federal Highway Administration, assist the American Association of State Highway and Transportation Officials with developing a requirement that concrete bridge structures be designed to accommodate reasonable estimates for interface shear demand, the cohesion contribution of interface shear capacity, and the clamping force across the interface shear surface. There are 5 to the Florida Department of Transportation. Revise your plans preparation manual to require that the qualified independent peer review for Category 2 bridge structures include checking and verifying the design calculations used for all nodal forces. Revise your plans preparation manual to require the engineering firm or company independently peer reviewing bridge design plans to submit a pre-qualification letter showing that it is qualified in accordance with Florida Administrative Code Rule 14-75 before permitting the firm to sign and seal the 100% certification letters indicating that the bridge designs have been peer reviewed. Revise local agency program agreements to specify that when structural cracks are initially detected during bridge construction, the engineering of record, construction engineering inspector, design build firm, or local agency that owns or is responsible for the bridge construction must immediately close the bridge to construction personnel and close the road underneath. Fully support the entire bridge weight using construction techniques that do not require placing workers on or directly under the bridge during installation, and restrict all pedestrian, vehicular, and construction traffic on the bridge until the complete support is in place and inspected. The last one to the Florida Department of Transportation, to help facilitate compliance with Florida Department of Transportation standards, require your personnel to monitor and inspect all local agency program bridge projects determined by the department to have uncommon designs. And final, add a discussion about redundancy to the structures manual, structures design guidelines, emphasizing uncommon bridge designs as determined by the Florida Department of Transportation. There are 3 to the American Association of State Highway and Transportation Officials. The first is work with the Federal Highway Administration to develop a requirement that concrete bridge structures be designed to accommodate reasonable estimates for interface shear demand, the cohesion contribution of interface shear capacity, and the clamping force across the interface shear surface. The second to AASHTO is added discussion about redundancy in the design of concrete structures to Section 5 of the LRFD, the Load and Resistance Factor Design, Bridge Design Specifications. And the last, added discussion about redundancy to the LRFD, again, the Load and Resistance Factor Design, Guide Specifications for the design of pedestrian bridges, emphasizing uncommon bridge structures. Finally, there are two recommendations to FIGG Bridge Engineers, Inc. The first, to train your staff on the proper use of P sub C, parentheses, the permanent net comprehensive force normal to the shear plane when calculating nominal inner surface shear resistance. And the second, institute a company policy to obtain a pre-qualification letter before finalizing any peer review contract with any engineering firm or company being considered to conduct peer review services.
Thank you very much, Ms. Bryson. Are there any amendments from the board members for the recommendations? And staff, I understand that you have something for the board's consideration. Let's do one at a time.
Certainly. Again, after the draft report went to the board, we recognized that we'd left one component out of a recommendation. That was the recommendation to the Federal Highway Administration. It has a companion rec, but I'll deal with number one first. We would propose the changed recommendation to say, assist the American Association of State Highway and Transportation Officials with developing a requirement that concrete bridge structures be designed with reasonable estimates for interface shear demand, the cohesion and friction contributions to interface shear capacity, and the clamping force across the interface shear surface.
Okay, thank you. So you're just cleaning up that one. You're really adding in friction. You're adding in friction basically there in that to talk about the cohesion and friction contributions to interface shear capacity.
That is correct.
Pretty much so. I'll certainly entertain a motion from my colleagues to adopt that, Vice Chairman, and as Vice Chairman's moved and Member Hamady seconded, to adopt that into a motion. Any discussion?
Again, as you clearly stated, the discussion of interface shear capacity does include cohesion and clamping forces, but also includes friction, and we had not included that in the recommendations, so that's why we added it.
Thank you. Any other discussion? Okay, it's been moved and seconded to adopt the motion amending the Federal Highway Administration, the rec to the FHWA. All in favor of adopting that motion, please signal with a hand and say aye. Opposed, there are none. That motion to amend that that recommendation to FHWA, that has been adopted unanimously. And I believe you have one additional one, perhaps.
Certainly. Mr. Chairman, we have the companion rec that goes to the American Association of State Highway and Transportation Officials. We would like to make a, parallel change, and I will read the proposed language. Work with the Federal Highway Administration to develop a requirement that concrete bridge structures be designed with reasonable estimates for interface shear demand, the cohesion and friction contributions to interface shear capacity, and the clamping force across the interface shear surface.
Okay, thank you. Basically, that is the companion rec to what we just approved. The first one that you read was to AASHTO to work with, for Federal Highway to work with AASHTO. This is for AASHTO to work with Federal Highway, and you've just, like in the other one, you've just cleaned it up to talk about the cohesion and friction. Okay.
That's correct, Chairman.
Thank you. Is there a motion to adopt that? The Vice Chairman has moved. The Member Hamady has seconded. Any further discussion? Seeing none. All in favor of adopting that motion to AASHTO, please signal with a hand and say aye. That motion does pass unanimously. Now we need to go back and adopt the recommendations as amended. Is there a motion to adopt the recommendations as amended? The Vice Chairman has moved. Member Hamady has seconded. No further discussion, I assume. All in favor of adopting the recommendations as amended? Please signal with a hand and say aye. The recommendations have been adopted unanimously as amended. Does anyone have any additional issues for discussion related to this report?
No.
Is there a motion to adopt the to adopt the report as revised? Member Hamady has moved. The Vice Chairman has seconded. Any discussion? Okay, all in favor of adopting the report as amended, please signal with a hand and say aye. The motion to adopt the final report has been passed unanimously. Do any members wish to reserve the right to file a concurring or dissenting statement? Member Hamady, the Vice Chairman Landsberg, so noted. You want to break for lunch now? Okay, all right. This final report, the draft report, is just about 200 pages in length, double-spaced pages. Staff will go and clean it up, adopt the amendments that we've just made, and it will be published on our website. We try to get them published in their final form in about 3 weeks. Meanwhile, we will be putting out a summary press release in just a few hours to summarize the report, the findings, the probable cause, and the recommendations as just adopted. In closing, I want to thank the staff for all of your hard work. I was there with you just for 2 days and saw what you were facing with, and I'm very proud of you for your hard work and dedication to improving safety. Certainly want to thank my colleagues for your hard work and preparation going into the board meeting and for the good discussion. Special thanks to Robert Aceta, investigator in charge, and the rest of the investigative team. It is truly a team effort. We always talk about the investigators, but we have to realize that nothing around here is just a solo effort. It takes support staff and program staff. We couldn't do all of those things without their support, so thank you for them as well. FIGG Bridge Engineers severely underestimated the demand on the bridge and significantly overestimated the bridge's capacity. And they incorrectly determined the bridge to be a redundant structure, among other calculations. But another structure failed in this accident, the structure of the public safety oversight. This structure should have ensured that qualified, independent firm provide effective peer review of the bridge plans as required. Louis Berger was not qualified and produced an incomplete report. When cracks in the bridge work reached unacceptable levels, the oversight structure should have resulted in suspension of work and in road closures, and it did not. Oversight of the project, like the bridge itself, collapsed. Today's recommendations, if acted upon, will ensure that in the future, additional guidance will allow designers to better determine loads, that plans will undergo peer review by qualified independent firms, that proper action will be taken anytime structural cracks are noticed, that uncommon designs will receive appropriate attention from the Florida Department of Transportation to ensure compliance, and that discussions of redundancy are included in manuals and guidelines, especially in relation to uncommon designs. These recommendations will make it less likely that an error will be made and even more likely that an error will be caught before concrete is even poured. Furthermore, they will make it more likely that structural cracks will trigger urgent actions to avoid injuries and loss of life. We stand adjourned.